Hello, everyone. So that's one of the last session of today. So I'm going to try to entertain you and not to be too boring. BPMN, streams and microservices. Those are often opposed, and I must confess, I don't know if in the Blade Runner movie, androids dream of electronic ships, but at Quicksign, we kind of dreamed of BPMN and streaming for our microservices architecture. And that's what we actually implemented at Quicksign. It may seem incompatible at first glance, but it actually works really well together. So I'm Vidal, Quicksign's CTO, and I'll try to give you a feedback of why we did it and how we did it. First, why BPMN? BPMN, if you don't know it, stands for Business Process Modeling Notation. It allows to modelize state and transitions. But it has bad press. I mean, usually it appears kind of dusty, scary, complicated, you name it. It's confused with UML. Oh, even more scary. Developers would rather code it using their favorite language rather than using a BPMN engine. So why would you use it? Well, let me explain first what we do at Quicksign in order to understand why we chose to use that. We do digital onboarding. We are not very well known from the public. Indeed, we are a B2B2C SaaS solution in white label, which means that you quite never see us, even if you have most likely used us to onboard using some online banks such as Boursorama Bank or Orange Bank. But under the hood, we are actually the European leader in digital onboarding for financial services. We drive most of French consumer finance, health management, and online banking digital onboarding processes. So I said Boursorama Bank, Orange Bank, but we also have BNP Paribas, which is, I think, in the room, RCI, Swiss Life, AXA, etc., to name only just a few. And they don't have the same requirements. They are all different. Business-wise, the regulations are complex and depend on the product and the country. They have different strategies and risk tolerances, which are reflected in their onboarding processes. And from a technical standpoint, they have different levels of maturity. Technically, not everyone has the latest reactive stack, you know what I mean? Some want to do REST, some want to do SOAP, synchronous or asynchronous, push, pull, you name it. And we want to onboard our customers on our solution progressively. Start small with a simple subscription workflow, then gradually optimize as a gain understanding, because our business is complex and even our customers have a hard time understanding it at first. So we start simple. And technically, start with a simple synchronous API, then move on to more sophisticated asynchronous API when they have the proper stack. Hence BPMN, which is why we chose it. Here is an example of what it could look like. It's actually a real one from one of our processes. We have many ones, but it's one of them. You can do long-running processes which represent states and transitions. It can last, I mean, at least for us, it can last from 5 minutes. If our AI detects that it is a passing case, or up to 3 months if the signer forgets some documents. It is a simple XML file stored in Git, versioned, so that we can roll out new iteration of our customers' workflows quite easily, and we can even have multiple versions of the workflows for our different customers. Well, BPMN is the heart of our architecture, and Kafka is the backbone. It's a backbone of our microservices architecture. It does, well, everything on our platform goes through Kafka. Why such a choice, Kafka and Streams? I mean, we are not Twitter. Twitter handles 500 million tweets per day. That's gigantic. At Quicksign, we currently handle 1.3 million audit trace entries per day. It's quite a lot, but it's 400 times less than Twitter. And for Twitter, I actually compared what I can compare, because I'm talking about tweets, but I don't really know under the hood for one tweet how many technical log entries it means. Anyway, we have a much less throughput. So where would we use the same tech? Well, we grow. We are now handling millions of digital subscriptions per year at a 70% annual growth rate. And now, the digital channel for digital onboarding is critical. It has to work. You know what I mean. Today, online applications need to just work. If you have latency, you lose your customers. And when we are talking digital onboarding, at the end of the workflow, you have somebody actually paying something. So you don't want, and actually subscribing to something for the long run. I mean, when you subscribe to a bank or an insurance, it's not for a month, it's for years. So when somebody is currently doing a subscription workflow, you don't want to lose him. So we need an architecture strong and able to scale. And we need traceability. We have a regulated business. Our signature is certified to the highest qualification level in Europe. It's called ETSI 319-411, for those in the room who might be interested in that. Anyway, we need to be able to prove conformance. If the judge, if there is a litigation and the judge asks for proof, we need to be able to give him that proof. So we need to keep the logs of everything that goes through our platform in a non-repeatable way. Non-repeatable means that we must prove that it has not been altered. CQRS-ES. It's a very important pattern that we use at Quicksign to enforce that traceability and that non-repeatability. It stands for Common and Query Responsibility Segregation with Event Sourcing. What is it? Well, I mean, traditionally, in a typical application, when the user requests something from your system, you have a controller which validates the request, makes decisions, and takes action on your database, all in one. So you don't have traceability, or if you have a trace, it's a trace after the fact. So nothing actually guarantees that what's in the log is actually complete. Instead of doing that, using the CQRS pattern, you explode that single box in many little boxes, in many steps. The first one is when the user requests something for your system, it generates a command, which is an object, which can be or well, for us, it doesn't necessarily need to be stored somewhere, but you can if you want, since it's an object, it's a message. It's evaluated by a command handler, like does the validation, takes the decisions, but instead of taking action directly on the database, the decisions that it makes are materialized as events, which are stored in an event store, which is, for us, a Kafka topic. Then, that Kafka topic, in which we store the events, is read by an event handler, which is a Kafka Streams processor, which consumes each and every events and updates, materialize those events onto an aggregation route. In an aggregation route store, which is a key value store implemented using RocksDB, because it is a default key value store integrated, available in Kafka Streams. The command handler, I'm back to the command handler. In order to take a decision, you often, most likely, will need to query the previous state of your aggregation routes in order to take the decision. You cannot just take decision based only on the event, on the command at hand. Using that pattern, you simply query the aggregation route store. You read from it the previous state in order to take your decisions. And which is why one of the constraints of a CQRS-ES architecture is that you want to process all the commands and events related to a given aggregation route sequentially, so that when you read, well, there are many reasons, but one of the reasons is that when you read the previous state from your aggregation route store, you are sure to read the previous state before evaluating a new command regarding that aggregation route store. Sorry, regarding that aggregation route. Another use case of a CQRS-ES architecture is, it's more like a Kappa architecture pattern, which is related to Kafka, is that you can consume those events, but instead of only updating aggregation routes, you can create, derive, materialized views optimized for some queries. For example, if you want to do some full text search, you can materialize your events in an Elasticsearch cluster in order to query it, or using Kafka Streams with its embedded RocksDB key value store, you can store, that's what we do, a JSON representation of the state of your processes. Which means that on the query side, which is why CQRS-ES stands for separation of commands and queries. On the top, in red, you have the write side, in green, the read side. The read side will be very fast, very low latency, very optimized for the kind of query that you want to do. You're going to use a store optimized for the kind of query that you use, whether it is full text search or a graph database. How does BPMN fit in? Well, it's actually a Saga pattern implementation. There are two styles. The orchestration style, which is the simplest. When you execute your BPMN process, when you execute an activity, you simply call a remote microservice using some kind of RPC call. You get the result, and based on the result of your call, you take action and decide whether you want to approve or reject your, in that case, your order creation request. The other, oh, sorry, I didn't, okay, here's our RPC. The other kind of the other kind of style of Saga pattern is a choreography style. In that style, you emit domain events. Instead of calling a microservice using RPC, you emit an order-created event, which is to a Kafka topic, which will be interpreted by some microservice and will reply the outcome of the request using another event, which our BPMN process will listen for and take action upon receiving the results. So here, if it receives a credit reserved event, it's going to approve the process. If it receives a credit limit exceeded event, it's going to reject the process. By the way, that terminology and diagrams are inspired by the website microservices.io, I think, or .org. I don't remember the extension. So the Saga pattern implementation. Simply, in microservices, yesterday, Cyril Martin was talking about service boundaries. Well, you can implement one of your microservice, one of your boundary, using a BPMN engine, or multiple microservices using BPMN engines, which communicate between them using events or using RPC. Often, BPMN is presented as incompatible with the microservices approach, but they're really not. Microservices is about decoupling, about separating your whole application into boundaries. Simply, if one of your boundaries is workflow-oriented and has some long-running workflows, hell, why not use a BPMN engine? It works perfectly well. So, in our architecture, we do online subscription. As I told, it can last from 5 minutes to 3 months, even 4 months. So it's very long. We need to keep track of where we are in the process, in what state we are in order to decide what to do next. And all our customers are different, so we have many different BPMN processes. But a BPMN engine, a classical BPMN engine like Camunda, which for us is one of the best BPMN engine on the market today. We love it. The editor is great. I mean, it's one of the first online HTML5 based editor that we use and just works well. It wasn't the case for many years. And the Camunda engine is great. It's open source. It's easy to debug, easy to understand. The code base is clean. But it has been implemented on a traditional database-based model. You have JDBC. It's blocking. I'm not too much going to talk about blocking versus non-blocking. It's not the topic of the talk. But you want to do, if you want low latency and scalability, non-blocking is better. Camunda is not. It's fully blocking. It's fully JDBC based. But we needed at Quicksign a way to scale it nevertheless. So we implemented the Kappa architecture and CQRS-ES, the separation of commands and queries on top of Camunda using Kafka. We separate the write interface and the read interface. The write interface generates commands which are sent to Camunda. When Camunda executes its BPMN process instance, it calls one of the microservices that are available in our platform, such as, for example, our OCR engine. I mean, we do digital onboarding, so we need to OCR our documents. Our fraud detection algorithms, or simply our signature services. Each and every of those activities are microservices deployed independently. By the way, we are in Kubernetes, which works great for us. And sometimes you have async replies. Some of our microservices are synchronous, others are asynchronous. Anyway, our Camunda engine generates technical events in using an SPI, which is available in Camunda, that we leverage to generate all the technical events, tracing the move of the token in the process instance to a topic in Kafka that we listen to. We could use it for simple use cases like indexing it in Elasticsearch to do full text search, and actually that's what we do. But a more interesting use case is that we listen to this topic using a Kafka Stream processor in order to compute, to materialize JSON representations of the current state of our process instances. In the key-value store, which means that when you query the key-value store using our read interface, you don't go through the whole Camunda stack. You don't go through its REST API. You don't go through the Java stack. You don't go through the database. You go straight in memory to the key-value store. So it's amazingly low latency. It's very fast. Why Kafka? It works, I mean, as a general observation, Kafka works for extremely massive big data use cases. So we figured it should easily handle our CQRS-ES based workloads. But as I said, we needed to be absolutely sure about traceability. We needed middleware that we would be sure would be able to handle the load of our events, of our CQRS-ES events, and to rely on it, to be sure that it would work. And what's important for that pattern is that you need at least once guaranteed delivery. I mean, you don't want to lose messages, obviously. You need sequential processing per topic partition, because, as I said earlier, for a given aggregation route, you need to make sure that all the commands and events related to a given aggregation route are routed to or are processed sequentially to avoid any kind of concurrency issues, and to make sure that all those events are routed to the same processor instances. We wanted RPC-like low latency because we are not using Kafka for a big data use case. We are not using it to do analytics, at least not yet. We are really using it as a backbone of architecture, so we needed very low latency. Durability and replayability, because when you do event sourcing, you need to be able to, if you lose your state, you need to be able to read again all your events in order to recreate your state. But it's actually quite not enough. Here comes Kafka Streams. At first, well, Kafka Streams is a key to build an event-sourced architecture on top of Kafka. Without Kafka Streams, it's possible, but it's quite hard. Kafka Streams makes it much easier. It provides automatic offset tracking. I mean, in Kafka, all consumers can be at a different point in the stream. That's the strength of Kafka. All consumers can consume at their own pace. So they are not at the same point in the stream. The consumer needs, therefore, to keep track of that point, of that offset. And I mean, it's not that it's awfully complicated to track that yourself, but Kafka Streams does it for you. You don't have to do it yourself. It provides an embedded key-value store, so it's the key to materialize views. For example, for us, the current JSON representation of our workflows. It provides a rich streaming DSL with operators. You can do aggregations, joins. It's very important because when you are creating a report, for example, aggregating multiple aggregation routes, changing, aggregating stuff together, you need a DSL, a streaming DSL able to do that. Dynamic queries, which is provided by Kafka Streams, it's very important. It's the key to find where your data is located, because one of the strengths of Kafka is that everything is sharded. That's awesome to scale. But the big issue with sharding is figuring out where your data is. I'll explain later how it works. But first, how do you route your events? The trick in CQRS-ES is to make sure that all messages related to given aggregation route end up in the same partition. Let's say that, like here, you have an aggregation route in blue with the 3 elements that you want to create. Let's say, that you have a M1 message that comes through, which represents the creation of that aggregation route. By default, if you don't give it a key, a null key, Kafka will use a simple round-robin algorithm in order to select the next partition where to route your message. So here, you get your M1 message, which creates the aggregation route. So let's say that we can say that the aggregation route is going to be pinned to the C1 consumer, hence to the P0 partition. Let's say now, so everything's fine. Let's say now that you want to modify your aggregation route to attach the orange D4 elements. And you have a M2 message to do just that. It does round robin. So it's going to end up on the next partition for that topic, which is a P1 partition. Luckily, the way Kafka allocated the consumers to the topics, to the partitions of the topic, the P0 and P1 partitions are consumed by the same consumer. So there you are lucky it works. The C1 consumer is going to be able to attach the D4 node to the D2 node. But now let's say that you want to do it again. The M3 message appears on the P2 partition, which is consumed by the C2 consumer, and there you have a problem. It breaks. So how do you make sure? And this is the hardest thing to understand when you want to do CQRS-ES with Kafka, is how do you route your events to the proper place? There are two strategies, two main strategies. The first is to use the aggregation route ID as the key. When the M1 message arrives, you give it the M1 key. So it is routed to the P0 partition, the C1 consumer, and the blue object is created. And when you publish the M2 and M3 messages, you need to give them the same key as the M1 message. So you give them the M1 key. So the M1, M2, and M3 message all have the M1 key. So, and when you do that, when you, in Kafka, with the default partition strategy, Kafka does the classical sharding algorithm, which is to create a hash of the key and do a modulo of the number of partitions. You're going to find that simple algorithm in almost all the sharded middlewares out there. It's very simple. That's one of the way to do it, but there is a problem, is with compacting. In Kafka, you want to be able to compact your topics to purge your old messages. And by default, it's based on the key. So it's gonna purge all the old messages of the same key. But you are mixing multiple types of messages with the same key. So this is usually not what you want. I mean, it might work for some use cases, but that's not what we did at Quicksign. What we did is to use a composite key with a custom strategy. We embed in, I mean, the first message, the M1 message, has the M1 key. But for the message M2 and M3, we embed M1 inside it. So the key of M2 might be M1, M2. And the key of M3 might be M1, M3. And you provide Kafka with a custom partitioner strategy, which extracts, so it's in the bottom left, which extracts the root key from the key. And creates a hash of the root key modulo the number of partitions, the same sharding algorithms. That way, you can make sure that all the messages related to an aggregation root end up on the same partition. This is very important. So at Quicksign, each time we produce events to a Kafka topic, we produce it with some kind of composite key, with a custom partitioner strategy, which is able to extract the root key from the key. How do you query your data? I've talked about that there are two cases. Either you use standard middleware, such as Elasticsearch, and it's easy. I mean, you don't even need to use really Kafka Stream for that, except if you want to do aggregation, which is useful. But you could use a simple Kafka consumer, and you feed your data. You materialize your data in your Elasticsearch cluster. Since it's a cluster, and the API handle the sharding out of the box, you simply query it. It's very easy. It's very convenient. It just works. So no big deal. But if you use Kafka Stream and its embedded key-value store, it's a bit harder, but it's not that hard and it has many benefits. So you store your state in an embedded RocksDB key-value store. Let's say that here, the data that you want to query is located in the P3 partition. But on your read interface, on your load balancer, you have absolutely no idea in which partition your data is. You just don't know. It's sharded. Here you have 4 partitions, but in a real use case, you could have hundreds or thousands. So you just tried in a round-robin fashion, randomly, actually. It's a random. You hit the first node, and you ask Kafka Stream. It provides an API, the interactive queries API, which tells you what is a node which owns the data that you want. Either you are lucky and you are on the right node, in which case you just return the data, or you are not. If you are not, you forward using some proxying mechanism of your choice to the proper nodes, to the proper node owning your data. Kafka Stream gives you an IP. So you have an IP, you have the IP of the node. So usually from the IP you can figure out what node you are talking about. There are some tricks sometimes. At Quicksign, I think we had to trick the mechanism a bit, because in the context of Kubernetes, you have local IPs and cluster IPs. So you have maybe some IP resolution, IP transformation to do, but usually you can figure out in what node your data is. And you forward it. And that time, when you arrive on the C2 node, you do the check again. You ask Kafka Stream again what node is the owner, and usually you should be on the proper node. But you need to check again, because if you're not lucky and in the highly low probability that there was a repartitioning, you might be, well, the data might have moved So you need to query again. In order to forward, you can use the RPC mechanism of your choice. You can use REST, RPC, gRPC, or whatever you want. Kafka Stream doesn't enforce the way to forward the query. How do I return state after a command? I showed, if you remember, the CQRS-ES slide where you had a command. And since everything is asynchronous in Kafka, how do you, in your command handler, in your request processor, in your REST API or whatever, how do you know what to reply to your client? Because it's easy to just fire and forget in Kafka. You just publish a message, but how do you wait for the outcome? How do you return the state related to the outcome specific to your commands? Well, you materialize the outcome to a Kafka topic. In a reactive fashion, using materialized view, you materialize the outcome and you wait for a specific correlation ID or timestamp, depending on your use case, by combining the Kafka Streams interactive queries I just showed you to query the proper consumer. And when you are on the proper consumer, you use the Kafka Streams key value non-blocking API to get the outcome, the state, and avoid blocking threads. Because in order to scale, some have different ideas, but I believe that if you are able to be non-blocking, it's much more scalable in performance, and you consume less threads. So, and using a very scalable architecture such as one based on Kafka and Kafka Streams, if you block your threads, I think it's a bit, it's a shame. But anyway, so Kafka Streams has a proper API to do it properly. It requires you some work. I mean, where were we crazy to do all that? It's a lot of work. Building an architecture using those patterns, using the CQRS-ES pattern on Kafka, I won't lie to you, it's some work. It's not suited for every business. We did it because it was important for our business. We needed traceability. It is of paramount importance to guarantee the completeness and the non-repeatability of our logs and to make sure that everything is in there. But it has a cost. It's more complex to implement. And at first, the developers in our team had quite right. But in the end, we are very happy. It was a ride, but worth the effort. We get a fully generated REST API from our business processes. I passed on that point quite quickly in the presentation, but from our BPMN engine, the REST API is fully generated. We don't code anything. That part only, generating a REST API from a Kafka stream, was quite a lot of work, but now we are very happy. We just model any workflow that we want, and we have the REST API, which is generated, a simple just API, which is generated directly. It can be synchronous or asynchronous. As I told you, we want to onboard our customers simply at first using synchronous APIs. So in our BPMN model, we can tell that some endpoint exposed is synchronous or asynchronous. And if it's synchronous, we can tell the criteria to return the result, to flush the response, in order to adapt to our customer's needs exactly when to give him the results. And we can do push or polling. We expose SEC We don't do WebSockets because SSE is easier to integrate for our customers, but we do push using SSE or polling using a standard REST API. So that was quite a ride. Is it crazy? I don't know, but we are very happy that we did it. And I'm done. And we have 5 more minutes if you have any remarks or questions or anything else. One question? Okay. Okay, 2 different views. Okay. When you do that, you need to pivot your keys. And Kafka Streams makes it pretty easy. You need to consume your 2 streams and to do some kind of correlation of your using the stream DSL, and to create an aggregated view by changing the key and routing your 2 aggregation routes on a same pivot key, so that your events are routed to the same partitions. Am I clear? That's kind of for example, I'm going to take an example that we have at Quicksign. Our customers want reports. Our business is to do so online signatures. We do those signatures for, let's say, for some financial institutions. So we need, let's say, daily to send a report of all the signatures that happened for a given financial institution. So we take all the we take all the events related to our cases and route them to using the key of the financial institution as a pivot key, so that all the events of all the online signatures end up in the same partition, so that you can process them sequentially and do your report. Obviously, there is something that you need to take care about is the cardinality of your keys. Because for us, when we use the key of our aggregation routes of our online signature, because at Quicksign, the pattern and the architecture that I showed to you is very well adapted to our business. I mean, it was like very suited, because at Quicksign, the aggregation route is one online transaction. I mean, when you sign, for example, you open an account at Boursorama Bank, it's actually one aggregation route. So we have hundreds of thousands of those per day. So you have enough cardinality to distribute the load in all your partitions of your Kafka cluster. But when you need to do some pivoting on a low cardinality key, for example, the financial institution, because at Quicksign we have like around 50, big institutions, so it's a very low cardinality. So you have the risk to have an unbalanced cluster, and you have the risk to have some nodes which receive all the events. So that's one of the things that you need to take care about and monitor to be sure that your cluster is evenly loaded. Well, I answered a bit more than what you asked, but hopefully that was clear enough. Do you have? Don't be shy. I don't bite. No other questions? Okay, we're done.